So this is the last part of 2D rigid body equilibrium. The smooth pipe rests against the wall at the points A, B, and C. Determine the reactions at these points needed to support the vertical force F. Neglect the pipe's thickness in the calculations. The following data apply. F is 135 newtons, theta 30 degrees, A is 40 cm, B is 50 centimeters, and C is 20 centimeters. And here's the given figure. So let's put the data in place. So theta 30 degrees. So the angle that this pipe here makes with the horizontal is also 30 degrees. 50 centimeters, 20 centimeters. The angle that between the vertical and this portion of the pipe perpendicular to this inclined plane is also 30 degrees. Take note of that by principle. So this is last part. So you should not be confused about angles anymore because you experience this from the very start of statics. So for the solution, I introduce an axis here. These are the reactions NA because the points of contact are smooth and the pipe is smooth. So NB perpendicular to this pipe here and NC upward perpendicular to the pipe. And I'll introduce this axis U, this axis V. So resultant RU should be 0. So NA is inclined with this inclined pipe 30 degrees. So therefore its component is NA cosine 30 equals the component of 135 is in the opposite direction of U and it is minus 135 sine 30. NB and NC are perpendicular to this U axis, so they have no components. From here we can solve NA. NA is equal to 77.94 newtons horizontally rightward. Next, to solve for NB so that we can solve directly NB without any simultaneous equation, we set moment C 0. So by the way, this distance is 20 tangent 30 because this is 30 degrees, tangent 30 is opposite over 20. Therefore, the opposite is 20 tangent 30. And therefore, this distance is 50 minus 20 tangent 30. So M sub C is 0, clockwise positive. So NB times quantity 50 minus 20 tangent 30 degrees. The component of NA parallel to the U axis is also clockwise. So that is NA 77.94 cosine of 30. Moment arm is 20 times 20. The component along the V axis in this direction downward is also clockwise and it is NA sine of 30. This is NA sine 30, this one. So plus 77.94 sine 30, the moment arm is 50 at C. Then minus 135 times this distance, this moment arm is 40 cosine of 30. So again, this is 40, this moment arm, 40 cosine of 30. So we can now solve NB. NB is equal to 35.84 newtons down to the right, 60 degrees with the horizontal. This one. This angle is 60 degrees with the horizontal, 30 degrees with the vertical. Then finally, we set moment B is 0. So this clockwise positive. So N sub C times quantity 50 minus 20 tangent of 30. Then this vertical distance of NA from B rather, is 20 over cosine 30, this vertical distance. So we will not resolve NA anymore because we can compute this hypotenuse. 20 divided by cosine 30. Cosine 30 is 20 over hypotenuse, so the hypotenuse is 20 over cosine 30. So plus NA 77.94 times 20 over cosine 30. Then minus 135. This moment arm, this distance, horizontal distance is 90 minus 20 tangent 30. This distance is 90 minus 20 tangent 30, then times cosine 30. So minus 135 times 90 minus 20 tangent 30 degrees times cosine of 30 degrees. So we have NC left using your calculator. N sub C is 191.7 newtons up to the left, 60 degrees with the horizontal. So let's check our answer by setting R sub V, computing RV. If it is 0 or close to 0, so that means all these answers are correct. So N sub C, 191.7 in the positive V direction, minus NB, minus 35.84, minus component of NA in this direction, NA sine 30, NA sine 30 minus 77.94 sine 30, and minus component of 135, which is 135 cosine 30, and it is equal to almost 0, so that means all these answers are correct. Compute the tension in the cable and the contact force at the smooth surface B when the 300 Newton meter couple is applied to the cylinder. Neglect the weights of the members. So let's have the free body diagram of the cylinder first. So we have the tension, normal, and the reactions at D. So summation moment D or moment D is 0. Then counterclockwise positive. So we have D times 0.085 meter. It should be 0.085 meter to be consistent with this couple here. Then minus 300 Newton meter equals 0. So because NB passes through D. So from there we can solve T equals 3529 newtons. Next, we do the free body diagram of portion ABD. Let's consider portion ABC rather. So this is the tension. We sum up we set moment at A0. These are the component reactions at A, which we will not name because they are not important because we set MA0. So counterclockwise positive. So we have NB times 100 mm. So it doesn't matter if it is 100 mm because the moment arm of 3529 newtons will also be in mm, which is 85 plus 100, so 185 minus 3529 times 185. So from there, NB can now be solved. It is equal to 6529 newtons. To test the deflection of the uniform 200-pound beam, the 120-pound boy exerts a pull of 40 pounds on the rope rig as shown. Compute the force supported by the pin at the hinge O. So here is the given figure. First, let's apply the weight of the beam, uniform beam of 200 pounds at its center of gravity. The length of the beam is 10 feet, therefore 5 feet from either end. So there's 2 feet here, so that means this is 3 feet. And because this is 8 feet, the weight of the boy is 4 feet from A also. And we have tension 40 pounds, so that will just cancel. This is also 40 pounds downward, and this is also 40 pounds downward. That's the effect of the tension on the beam. So reaction at A, NA, and reaction at O. So there's no horizontal component of reaction at O. It's downward, expected downward, because the tension will just cancel. This 40-pound force will just cancel. So set MA equals 0, counterclockwise positive, so we have RO times, clockwise positive rather, RO times 2, then everything is counterclockwise. So minus 200 times 3, remember this is 3 feet. Minus 120 times 4 feet. Minus 40 times 6. Minus 40 times 8. And we can now solve RO. RO is equal to 820 pounds downward. Rod AB is acted upon by a couple M and two forces each of magnitude P. Derive an equation in theta, P, M, and L that must be satisfied when the rod is in equilibrium. Then determine the value of theta corresponding to equilibrium when moment is 150 Newton meter, P 200 Newtons, and L is 600 mm. So here is the given figure. Let's put the reactions at C, although we will not name them. So this is L, because this is theta, so this is L cosine theta. And this distance is L sine of theta. So we set MC is 0, clockwise positive. So we have M and minus P times L cosine theta minus P times L sine theta. So we cannot derive M. It is factor out PL times quantity cosine theta plus sine theta. So that's the equation. And in part B, moment is 150 Newton meter, P 200, L 600 mm, but we should make it 0.6 meter to be consistent with Newton mm for a moment. So cosine theta plus sine theta equals 1.25. Now, you may set theta by trial and error, but it will take time, assuming you have no, or high-tech calculator is not allowed. So we change cosine theta to square root of 1 minus sine square theta. Then plus sine theta equals 1.25, or square root of 1 minus sine square theta equals 1.25 minus sine of theta, square both sides. So 1 minus sine square theta equals 1.5625 minus 2.5 sine theta plus sine square theta. Simplifying, so this is 2 sine square theta minus 2.5 sine theta plus 0.5625 equals 0. By quadratic equation, sine theta is negative of negative 2.5 plus minus square root of negative 2.5 square minus 4 times 2 times 0.5625 all over 2 times a, which is 2. So sine theta equals 2.5 plus minus the radical is square root of 7 over 2 over 4. So we can solve theta, set minus first for smaller value. Sine theta is 2.5 minus square root of 7 over 2 over 4, inverse sine of that value. So theta is 17.11 degrees. Then the other one, sine theta 2.5 plus square root of 7 over 2 over 4. So theta is arc sine of quantity 2.5 plus square root of 7 over 2 all over 4. So for that case, theta is 72.89 degrees, or they are supplementary from the equation shown. Determine the tension in the cable at B given that the uniform cylinder weighs 350 pounds. Neglect friction and the weight of the bar AB. So here is the given figure. First, let's draw the FBD of the cylinder. It weighs 350 pounds. And of course, we have reaction, normal reaction at D and normal reaction at C. Then the angle that ND makes with the vertical is also the angle that this bar makes with the horizontal, because ND is perpendicular to this bar. So ND and the vertical should also form angle of inclination 40 degrees. Then let's solve for N sub C. By the force triangle, we have 350 pounds, then ND, which makes 40 degrees, then horizontal N sub C. So horizontal, vertical, so this is 90 degrees. Tangent of 40 equals N sub C over 350. So N sub C is 350 tangent 40, or it is equal to 293.7 pounds. Then we draw the free body diagram of this bar. And because we have to transmit ND here, so we'll just consider, uh, we ignore the internal force, which is ND. Let's just consider NC and the applied force 350, the applied weight. So since this is 40 degrees, this angle is 50 degrees. And because this is 90-degree angle equal to this angle here, in other words, this is radius, this is the common hypotenuse, radius, common hypotenuse. So therefore, this 50 degrees must be bisected by this line here through the center of the cylinder. So each is 25 degrees. 50 degrees divided by 2. So that we can compute this distance here. Tangent of 25 equals 3 feet over this distance. So this distance is 3 over tangent 25. Then let's call that the tension. Then component reactions at A, we will not name because our equation is moment at A 0. Considering counterclockwise positive, so it is T, it is equal to T times 10.5 minus clockwise moment, so N sub C 293.7 times 3 over tangent 25 degrees, then minus 350 times 3 feet, radius of the cylinder. So from there you can solve for T. T is equal to 280 pounds. Determine the external reactions at A and F for the roof truss loaded as shown. The vertical loads represent the effect of the supported roofing materials, while the 400 Newton force represents a wind load. Here is the given figure. We observe that the vertical loads are symmetrically applied because they are equally distant from the center G, 500, 500, then 250, 250. So observe the symmetry. So we also 400 Newton force can be moved along its line of action at G. So they will be combined horizontally at G and vertically at G. So we'll remove them first, replaced by a simple system. Let's begin with the vertical load. The vertical load is 500, 500, 500, 15 plus 250, 250, 2000, plus the vertical component of 200, which can be combined with 2000 here, which is 400 sine 30. So 400 sine 30 is 200 plus 2000, so 2200 newtons downward. The horizontal component of 400 is also shifted along its line of action by principle of transmissibility of a force at G, horizontally to the right 400 cosine 30, and that is 346.4 newtons. Then let's put the component reactions at A, leftward and upward, and at F, upward. So first, Rx0, and it is equal to 346.4 minus AX. So therefore, AX is 346.4 leftward. Then set moment F0, clockwise positive. So we have AY times 10 minus 2200 times 5 only, because 346.4 and AX pass through F. So therefore, MF equals, or AY equals 1100 newtons upward. By symmetry, we expect RF to be 1100 newtons also upward. Moment A0, counterclockwise positive, so equals RF times 10 minus 2200 times 5. So RF is also 1100 newtons upward. Determine the magnitude and direction theta of the minimum force P needed to pull the roller of mass M over the smooth step. The following are the given data. A is 600 mm, B is 100 mm, theta 120 degrees, M is 50 kilograms. Here's the given figure. Then let's enlarge it, showing the data. So theta 120 degrees. This is the reaction at B, which will pass through the center of this ruler because the system is frictionless. Then the radius is 600 mm, and because this is 100 mm, this distance is radius 600 minus 100, so 500 mm. Then because that's a 90-degree triangle there, so this is square root of 600 squared minus 500 squared, 31.66 mm. Then let's resolve P into components parallel to the incline, P cosine theta, and perpendicular to the incline, P sine theta. And the angle between the weight mg and the normal or weight mg vertical and this normal line or axis perpendicular to the incline is also 20 degrees. So set moment B0, then it is clockwise positive, so P cosine theta, let's make 500 mm to 0.5 meter. So P cosine theta times 0.5, P sine theta is also clockwise, so plus P sine theta times 0.33166 meter. Then this weight mg is resolved into two components, one horizontal in this direction, so it produces counterclockwise moment. So minus mg, this component is mg sine 20, then moment arm 0.5. Then the component perpendicular to the inclined is mg cosine 20, then moment arm minus also, it is counterclockwise, minus mg cosine 20 times 0.33166. So factor out P, we have P quantity 0.5 cosine theta plus 0.33166 sine theta equals combined 0.5 sine 20 plus 0.33166 cosine 20 in terms of mg, 0.4827 mg. So P therefore is 0.4827 mg over quantity 0.5 cosine theta plus 0.33166 sine theta. So take note that the numerator is constant because m and g are constants. So we minimize P by differentiating it with respect to theta. So remember, derivative of P fraction is denominator derivative of numerator 0 minus numerator times derivative of denominator 0.5 times negative sine theta plus 0.33166 derivative of sine is cosine theta all over denominator square. Then we set the derivative to 0 because we minimize P. So 0 times denominator square is 0 divided by this constant negative 0.4827 is 0 also. So that means these terms in the parentheses should be set to 0, negative 0.5 sine theta plus 0.33166 cosine theta is 0. So that means tangent theta is 0.33166 over 0.5. Then from there, we can now solve theta, arctan of this fraction. So theta equals 33.56 degrees. For the minimum P, substitute into this formula here. M is 50, G 9.81. Divided by 0.5 cosine of 33.56 degrees plus 0.33166 sine of 33.56 degrees. So minimum P is equal to 394.6 newtons. The window washers A and B support themselves and the 30-pound uniform plank CD by pulling down on the ropes. Determine the tension in each rope and B, the vertical force that each man exerts on the plank. So here is the given figure. So let us say the washer A exerts tension A. So that's the weight of the plank, 30 pounds. The length of the plank is 16 feet, so from either end 8 feet. So therefore this is just 2 feet to make it 8 feet from D. So the tension exerted by washer A is TA. Therefore, the force that it will exert on the plank will be 170 minus TA, or that's the normal reaction on his feet. Then tension for washer B is T sub B exerted, so therefore the transmitted force here on the plank would be 190 minus T sub B. And this is also tension A, this is tension D, tension B. So first is we set considering the plank anymore. So we do not consider that anymore because they are already included in this transmitted force on their feet respectively. So considering the plank, moment D is 0, clockwise positive, so we have equals T sub A times 16, then minus 30 times 8, minus quantity 170 minus TA times 6, then minus quantity 190 minus T tension B times 4. So simplifying, 16, then negative 6 TA, so that would be 22 TA, then plus 4 tension B equals 30 times 8 plus 170 times 6 plus 190 times 4, and that is 2020. Call that equation 1. Then we set moment B 0, considering the plank, FBD or the plank. So clockwise positive, we have T sub 8 times 12 minus 30 times 4 minus quantity 170 minus TA times 2, then minus T sub B times 4. So simplifying again, 12 TA, then negative 2 TA, so that's 14 T sub A, then minus 4 T sub B, sorry, 16 minus 4 T sub B, then equals 30 times 4 plus 170 times 2, that is 460. So adding equations 1 and 2, so we have 36 T sub A equals 2,480. So T sub A can now be computed. It's equal to 68.89 pounds. And substitute in equation 1, 22 times 68.89 plus 4 T sub B equals 2020. So T sub B can now be computed. It is equal to 126.1 pounds. For part B, the vertical force that each man exerts on the plank, it is NA represented by 170 minus TA. So minus 170 minus 68.89 is equal to 101.1 pounds. Then NB is 190 minus 126.1. So it is equal to 63.9 pounds. A slender rod AB of weight W is attached to blocks A and B that move freely in the guide shown. The constant of the spring is K and the spring is unstretched when theta is 0. Letter A, neglecting the weight of the blocks, derive an equation in W, K, L, and theta that must be satisfied when the rod is in equilibrium. Then B, determine the value of theta when W is 75 pounds, length is 30 inches, and K, spring constant, is 3 pounds per inch. So for the first free body diagram, tension in the spring is K times delta S, and we have NA and B, which should be rightward. Then intersection between NA and NB, because we plan to set moment at O0 so that they are not involved. Then this moment arm is L over 2 cosine theta. Then this one is L sine theta. And this one is L cosine theta. So because the spring is unstretched when theta is 0, and when it is stretched, the final length, the it is stretched because originally this end was here. It was L. Then this is now the final position of A. So therefore, the stretching here is L minus L cosine theta. That's the final displacement. SO is 0, and final displacement is L. When A was here, it was L horizontal. Then it moves to the right. That's why the final horizontal projection is L cosine theta. So that means this delta S here final, or S final, is L minus L cosine theta, or L times 1 minus cosine theta. Since SO is 0, delta S is also SF, which is L times 1 minus cosine of theta. So MO K delta S therefore is KL times 1 minus cosine theta. So set MO 0, counterclockwise positive. So we have K delta S, or KL 1 minus cosine theta times L sine theta, moment arm. Then minus W times L over 2 cosine theta. So cancel out L. So we have KL 1 minus cosine theta times sine theta equals W cosine theta over 2. So rearranging, we have W 1 minus cosine theta sine theta equals W over 2 KL. Or W over 2 KL equals 1 minus cosine theta quantity times tangent theta. So that's the derived equations, part A. For part B, we set W equals 75, 1 minus cos sine theta tangent theta equals 75 over 2 times 3 times 30. So distribute tangent theta, tangent times cosine is sine. So tangent theta minus sine theta equals 5 over 12. So it's easy to solve theta by trial and error. So solving for theta by trial and error, theta is equal to 49.706 degrees. A uniform rod AB of length 2r rests inside a hemispherical bowl of radius r as shown. Neglecting friction, determine the angle theta corresponding to equilibrium. So here is the given figure. So first, let's apply the weight which is acting at the center of gravity, G. Then distance from A to G is R. G to B is also R. Then we have here the diameter, which is 2R. Then from geometry, this angle, this inclined plane, and this one with the diameter is a 90-degree angle here. And if you do not know that, that's your problem, because this is statics and we just use geometry. So remember that in a circle, chords joining the ends of the diameter form 90 degrees, or they are perpendicular to each other, because this is a peripheral angle and this is 180 degrees. So therefore, this is half of 180 degrees. Any point here connecting the ends of the diameter are perpendicular. Chords joining the ends of the diameter are perpendicular to each other. And you should know that. That's the trick here. That's why this is a level 50 problem. So this is NA. Because frictionless, NA passes through the center of the ball, sphere, or center of the circle. And you should know also that. And therefore, that's radius. This is NB perpendicular to this inclined. They meet as well as the weight at that point because the system is in equilibrium. Remember, forces involved in the free body diagram of a body that is in equilibrium will close or will meet at the point, or when we draw the first triangle, it closes. The triangle closes. So this is also theta, the angle between this bar and this rod and the horizontal, which is given here. Since from A to this point, this is the angle of inclination is theta, so the angle between the vertical and the normal to the inclined plane is also theta. Remember that. So this is the center of the bowl or hemisphere or the circle. Then distance from A to center is radius. Center to this point is, I'll just call this NB, although there B is there. This should be another point, but let's just call that NB. So ND. So since this is radius, and one angle is theta, so the measure of this angle is also theta because this is an isosceles triangle. So therefore, the angle that the line of action of NA makes with the horizontal is 2 theta. Since this is vertical and this is horizontal, this measure is 90 minus 2 theta. So constructing by the way, this is hypotenuse 2r times cosine of theta. And this distance is from A to G is r, and the angle is theta, so this is r cosine theta. So drawing the fourth triangle, we have weight, then ND, then NA. The angle between the weight and ND is theta, and ND and the weight is theta, and NA and the vertical W is 90 degrees minus 2 theta. Therefore, this remaining angle is 180 minus theta minus quantity 90 degrees minus 2 theta. So this angle here is 90 degrees plus theta. So to check, if you add all the angles, it should add up to 180 degrees. So by sine law, NB as to sine 90 degrees minus 2 theta equals weight as to sine of quantity 90 degrees plus theta. ND. So therefore, ND is equal to, because sine 90 degrees minus 2 theta is cosine 2 theta, and sine quantity 90 degrees plus theta is cosine theta. So remember, sine 90 cosine theta, sine 90 is 1, cosine theta, so 1 times cosine theta is cosine theta, plus cosine 90 which is 0 times sine 90, sine theta, so the second term is 0. Sin cos plus cosine, remember. So sine of complementary angle is cosine of the complementary angle. That's why it's cosine 2 theta. Sine of 90 minus alpha, for example, is cosine of alpha, so cosine of this angle here. So therefore, NB is W cosine 2 theta over cosine theta. Then we consider this free body diagram. We set moment A0 counterclockwise positive. So we have NB times 2R cosine theta. Then minus W times R cosine theta equals 0. So divide everything by R cosine theta. Then we say NB. We can derive NB equals W over 2. So equate these two. W cosine 2 theta over cosine theta is W over 2. We cancel W, so 2 cosine 2 theta equals cosine theta. From trigonometry, cosine 2 theta is 2 cosine square theta minus 1. So 2 times 2 cosine square theta minus 1, one identity. The other is cosine square theta minus sine square theta, but that's the same. The other is 1 minus 2 sine square theta. There are 3 identities for cosine 2 theta. You just review trigo. That's not part here because this is already statics. So simplifying, we have 4 cosine square theta minus cosine theta minus 2 equals 0. So by quadratic formula, A is 4, B is negative 1, and C is negative 2. So cosine theta is negative of negative 1 plus minus square root of negative 1 square minus 4 times negative 2 all over 2 times 4. So cosine theta is 1 plus minus square root of 33 over 8. So if we use minus, the value would be negative, so that's impossible. So we have to consider plus. Cosine theta is 1 plus square root of 33 over 8. So from there, we can now compute theta. It is equal to 32.53 degrees. So assuming high-tech calculator is not allowed. So you have to review also quadratic formula. Then there is another solution. This rod will be in equilibrium when the center of gravity is farthest from the top. Remember, when you have a lower portion, the body will be in equilibrium only when its center of gravity is farthest from the top. So that's the idea. So the second part is by calculus. This is equal to, considering this right triangle, the hypotenuse is 2r cosine theta, the angle opposite it is theta. So therefore, this is hypotenuse 2r cosine theta times sine of theta. And because from A to G is r, and the angle is theta here, so therefore this is r sine of theta. And I will call this distance from the top to G as yg, that distance yg. So let's maximize yg. Yg is 2r cosine theta sine theta minus r sine theta from the figure. So this is an alternate solution. Factor out r and take note that 2 cosine theta sine theta is sine to theta from trigonometry and minus sine theta. So maximizing yg means we have to differentiate yg in term with respect to theta. So it is r quantity, derivative of sine is cosine to theta times derivative of 2 theta with respect to theta is 2, minus derivative of sine is cosine theta, then set to 0. 0 over r is 0. So this is 2 cosine to theta minus cosine theta equals 0. Transpose cosine theta to the right, so 2 cosine theta equals cosine theta, which is the same equation here. Therefore, this will arrive at the same answer because the solution will be the same. So theta is really 32.53 degrees.